Okay, everyone, I'm so glad you're here for this module. I'm your host at Veterinary Epidemiology, and today we're diving into one of the most high-yield topics on the entire ACVPM exam, measures of association and effect. Whether you've been following along since the first module or you're jumping in here because this topic came up on a practice question and you thought, "Hold on, what is PAR again?" You are absolutely in the right place. In this module, we're going to walk through relative risk, odds ratios, rate ratios, attributable risk, population attributable risk, and the number needed to treat. We'll work through formulas, interpretations, and real veterinary examples, including a worked 2x2 table using BVDV and reproductive failure in cattle. We'll also spend time on the nuances that the ACVPM exam is known for testing, things like when OR approximates RR and what a confidence interval that spans 1 actually means. So let's get to it. Grab your pen, we're going to do some math together, and I promise you by the end of this session, these measures will feel like second nature. Second nature. Let's go. Calculate any measure of association, we need to set the foundation. Everything we do today, every formula, every interpretation flows directly out of a single 2x2 contingency table. Let's orient ourselves. The 2x2 table, sometimes called the fourfold table or the contingency table, is the workhorse of analytic epidemiology. It organizes data in a simple, elegant way that allows us to compare disease frequency between exposed and unexposed groups. Here's how the table is structured. Across the top, we have our outcome. Disease present in the first column, disease absent in the second column. Down the left side, we have our exposure status, exposed on top, unexposed on the bottom. This gives us 4 cells and we label them with letters A, B, C, and D. Cell A is exposed and diseased. Cell B is exposed and not diseased. Cell C is unexposed and diseased. Cell D is unexposed and not diseased. From these 4 numbers, we can calculate every single measure of association we'll discuss today. A few quick notes. The row totals give us our exposed group size, A plus B, and unexposed group size, C plus D. The column totals tell us total cases and total non-cases. Keep this layout locked in your memory. It is the skeleton of analytic epi. We have our 2x2 table clearly in mind. Let's move to the first and most intuitive measure of association, the relative risk, also called the risk ratio. The relative risk, or RR, answers a beautifully simple question. How many times more likely are exposed individuals to develop disease compared to unexposed individuals? It's a ratio of 2 risks, and it tells us the strength and direction of the association between an exposure and an outcome. The formula is RR equals the risk in the exposed divided by the risk in the unexposed. In 2x2 table notation, that's RR equals A divided by A plus B divided by C plus D. Interpretation is straightforward. The null value for RR is 1. That means exposure is not associated with disease. And RR greater than 1 means the exposure increases the risk of disease. And RR less than 1 means the exposure is protective. For example, an RR of 3 means exposed animals are 3 times as likely to develop the disease compared to unexposed animals. Critically, and this is a frequent exam point, RR is the appropriate measure for cohort studies, where we follow animals over time and observe who develops disease. In a cohort study, we can calculate true incidence proportions in both groups, making RR directly calculable and interpretable. We will revisit the study design measure linkage in a later slide, so hold that thought. Relative risk is elegant, but not always available to us, especially when we're working with case control data. That's where the odds ratio steps in. The odds ratio, or OR, compares the odds of exposure among cases to the odds of exposure among controls, or equivalently, the odds of disease among the exposed to the odds of disease among the unexposed. From our 2x2 table, the formula reduces very neatly to what's called the cross products ratio. OR equals A times D divided by B times C. Like the RR, the null value for the OR is 1. An OR greater than 1 suggests a positive association. An OR less than 1 suggests a protective association. The OR is the primary measure of association for case control studies, where we cannot directly calculate incidence proportions because we selected cases and controls deliberately. It's also the default output of logistic regression, making it ubiquitous in published veterinary literature. It applies equally to cross-sectional studies, where it's sometimes called the prevalence odds ratio. Here's the subtlety the exam loves: the rare disease assumption. When the disease outcome is rare, typically defined as less than 10% prevalence, the OR is a good approximation of the RR. But when the outcome is common, the OR will overestimate the magnitude of the association compared to the RR. This is a classic exam trap. The risk-based and odds-based measures. Now, let's talk about what happens when our study uses person time, or in our case, animal time, as the denominator. This brings us to the rate ratio. In some cohort studies, particularly those tracking disease over varying follow-up periods, animals enter and leave the study at different times or may be censored. In these situations, we calculate incidence rates using animal time denominators rather than simple proportions. The analog to the relative risk in this setting is the incidence rate ratio, or IRR, also called the rate ratio. The formula is IRR equals incidence rate in the exposed divided by incidence rate in the unexposed, where each incidence rate equals new cases divided by total animal time at risk. For example, if exposed cattle experience 40 new cases of mastitis per 500 cow years, their incidence rate is 0.08 per cow year. If unexposed cattle experience 20 cases per 400 cow years, 0.05 per cow year, the IRR is 0.08 divided by 0.05 equals 1.6. Exposed animals develop mastitis at 1.6 times the rate of unexposed animals. Interpretation parallels the RR exactly. Null value is 1. An IRR greater than 1 indicates a harmful association. IRR less than 1 indicates a protective one. The key difference from RR is conceptual. We're comparing rates, events per unit of time, rather than cumulative risk proportions. This distinction matters when follow-up time varies substantially across study participants. For the ACVPM exam, recognize when a scenario provides animal time data and understand that this calls for the rate ratio rather than the risk ratio. We've been thinking in relative terms: how many times more likely, how much higher the rate. Now we're going to shift our thinking to absolute measures, starting with the attributable risk. The attributable risk, AR, also called the risk difference, is one of the most practically important measures in epidemiology, and it's one that sometimes gets undervalued in discussions dominated by relative measures. It asks how much additional disease is caused by this exposure in absolute terms. The formula is simple. AR equals the risk in the exposed minus the risk in the unexposed equals, in our 2 by 2 terminology, A divided by A plus B minus C divided by C plus D. The AR is expressed in the same units as risk, usually as a proportion or percentage. If the risk of disease in exposed animals is 0.3 and in unexposed animals is 0.1, the AR equals 0.2 or 20 percentage points. That means 20% of the cases in exposed animals are directly attributable to the exposure, above and beyond the background rate. Why does this matter for public health? Because a relative risk of 10 sounds alarming, but if the baseline risk is 0.001%, the absolute excess risk is still tiny. Conversely, a modest RR of 1.5 on a high background risk disease could represent an enormous absolute burden. The AR helps us prioritize interventions based on how much disease we could actually prevent. This is why public health policy is typically driven by absolute measures, not relative ones. How much excess risk the exposure creates in absolute terms. Now let's ask, what fraction of disease among exposed animals is actually due to that exposure? That's the attributable fraction. The attributable fraction, AF, sometimes called the etiologic fraction, or EF, takes the attributable risk and expresses it as a proportion of the total risk in the exposed group. In other words, of all the disease occurring in exposed animals, what percentage can we attribute specifically to the exposure? There are two equivalent formulas worth knowing. AF equals AR divided by the risk in the exposed equals the risk in the exposed minus the risk in the unexposed divided by the risk in the exposed. Or equivalently, using the relative risk, AF equals RR minus 1 divided by RR. Let's work through an example. Suppose BVDV seropositive cows have a 40% risk of reproductive failure and seronegative cows have a 15% risk. AR equals 0.25, AF equals 0.25 divided by 0.4 equals 0.625 or 62.5%. This tells us that 62.5% of reproductive failure cases among BVDV seropositive cows can be attributed to BVDV seropositivity. The remaining 37.5% would have occurred anyway due to other causes. The AF is particularly useful in causal inference and in communicating the burden of a specific exposure to producers and policymakers. It's also a stepping stone to the population measures we'll cover next. Attributable fraction tells us about disease in exposed animals, but what about the whole population, exposed and unexposed together? That's where the population attributable risk and the PAF come in. The population attributable risk, or PAR, is one of the most powerful measures in public health epidemiology. It answers, if we eliminated this exposure entirely from the population, how much disease would we prevent? It accounts not just for the strength of the association, but also for how prevalent the exposure is in the population. The formula, PAR equals overall total incidence rate minus incidence rate in the exposed. The population attributable fraction, or PAF, sometimes written PAF percentage or AFPOP, expresses PAR as a proportion of the overall disease rate. PAF equals PAR divided by overall incidence rate times 100%. Here's a key insight. A highly prevalent but weakly associated exposure can have a higher PAF than a rare but strongly associated exposure. This is why routine vaccination for common pathogens, even with modest efficacy, can have outsized population impact. PAF is the measure that drives herd level and national disease control decisions. Another equivalent formula for PAF when you have exposure prevalence, or PE, and RR is Levine's formula. PAF equals PE times RR minus 1 divided by PE times RR minus 1 plus 1. Definitely worth knowing for the exam. Thinking about populations. Now, let's bring this to the clinical level, where individual treatment decisions are made. This is where the number needed to treat, or NNT, becomes invaluable. The number needed to treat, or NNT, is a measure of clinical effectiveness that answers a very practical question. How many animals do I need to treat with this intervention to prevent one additional case of disease? It's derived directly from the absolute risk reduction, ARR, which is simply the attributable risk flipped, the difference in outcome frequency between the control group and the treated group. NNT equals 1 divided by the absolute risk reduction equals 1 divided by the risk of the control minus the risk in the treated. A lower NNT means the treatment is more effective. Fewer animals needed to be treated to prevent one case. An NNT of 1 would be a perfect intervention. An NNT of 100 means you need to treat 100 animals to prevent just one case. The number needed to harm, NNH, is the inverse concept applied to adverse effects. How many animals need to be exposed to the treatment before one additional animal is harmed? It's calculated the same way, but using the absolute risk increase for the adverse outcome. Together, NNT and NNH allow clinicians to weigh the benefits and risks of a treatment quantitatively and communicate those trade-offs clearly to producers and clients. In herd medicine, these measures are especially powerful for economic decision-making around vaccination programs and prophylactic treatments. We've defined both RR and OR. Now, let's talk about one of the most frequently tested decision points on the ACVPM exam. When do you use which measure and why does it matter? Choosing between the relative risk and the odds ratio is not arbitrary. It's driven by two factors: study design and outcome frequency. Study design comes first. In a cohort study, we follow a defined population over time and directly observe who gets sick. Because we're tracking everyone from the start, we can calculate true incidence proportions in both the exposed and unexposed groups. This means we can and should calculate the relative risk. In a case control study, we start by selecting cases, animals that already have the disease, and controls, animals that don't. We then look backward to assess exposure. Because the proportion of cases in our sample is set by us, not the population, we cannot calculate true incidence and therefore cannot calculate RR directly. We use the OR instead. Outcome frequency is the second consideration. As we covered earlier, when the outcome is rare, less than about 10%, OR approximates RR. When the outcome is common, OR diverges from RR and overestimates the magnitude of association. In cross-sectional studies with common outcomes, the prevalence ratio, analogous to RR, may be more appropriate than the prevalence OR. calculated our measures of association, but a single point estimate, an RR of 2.4 say, tells us only part of the story. We need to know how much we can trust that number. That's where confidence intervals come in. A confidence interval, or CI, expresses the precision of our estimate. A 95% confidence interval means if we repeated this study 100 times under the same conditions, approximately 95 of those intervals would contain the true population value. Narrower intervals indicate greater precision, which comes from larger sample sizes and lower variability. Here's how to read CIs for measures of association. For the relative risk and odds ratio, the null value is 1. If the 95% confidence interval does not include 1, for example, RR equals 3.2, 95% confidence interval 1.8 to 5.6, the result is statistically significant at the alpha at 0.05 level. If the CI crosses 1, for example, RR equals 1.6, 95% CI 0.9 to 2.9, we fail to reject the null hypothesis of no association. For the attributable risk and other risk differences, the null value is 0. Don't conflate precision with validity. A very precise estimate, a very narrow CI, can still be wrong if the study has systematic bias. Validity refers to the absence of bias. Precision refers to random error. An exam question may describe a large study with a very narrow CI around a biased estimate. That's a precise but invalid result. Also important, p-values tell you whether an association is statistically significant, but not the magnitude or direction. Always report effect estimates with CIs, not p-values alone. The ACVPM exam will test your ability to distinguish statistical significance from clinical or epidemiological significance. This is a slide where we put it all together. Let's work through a realistic veterinary example and calculate every measure we've discussed today from a single 2x2 table. Get your pencils ready. Here's the scenario. A prospective cohort study follows 400 beef cows through a single breeding season. 200 cows are BVDV seropositive, exposed, and 200 are seronegative, unexposed. At the end of the season, reproductive failure is diagnosed in 80 seropositive cows and 30 seronegative cows. The 2x2 table, A equals 80, B equals 120, C equals 30, D equals 170. Let's calculate each measure step by step. The risk in the exposed, 80 divided by 200 equals 0.4 or 40%. Risk in the unexposed, 30 divided by 200 equals 0.15 or 15%. The overall risk, 110 divided by 400 equals 0.275, 27.5%. The RR equals 0.4 divided by 0.15 equals 2.67, meaning seropositive cows are 2.67 times more likely to experience reproductive failure. The OR equals 80 times 170 divided by 120 times 30 equals 13,600 divided by 3,600 equals 3.78. Note, the odds ratio is greater than the risk ratio because the outcome is common, 27.5%. The AR, the risk difference, equals 0.4 minus 0.15 equals 0.25, 25 percentage points. The AF, also known as the ideologic fraction, equals 0.25 divided by 0.4 is 0.625, or 62.5% of reproductive failure in seropositive cows is attributable to BVDV seropositivity. PAR equals 0.275 minus 0.15 equals 0.125 or 12.5 percentage points. PAF equals 0.125 divided by 0.275 times 100%, 45.5%, meaning eliminating BVDV seropositivity could prevent about 45.5% of all reproductive failure in this herd. NNT equals 1 divided by 0.25 equals 4, meaning you would need to protect 4 cows to prevent 1 case of reproductive failure. Notice the OR of 3.78 versus RR of 2.67. This is a textbook demonstration of OR overestimating RR when the outcome is common. If the exam gives you a scenario with a common outcome and asks which measure is preferred, always choose RR or the prevalence ratio for cross-sectional data over OR. Covered a tremendous amount of ground in this module. Before we close out, let's consolidate everything into the core takeaways you need to carry into your exam. 1. The 2x2 table is everything. Every measure of association, RR, OR, AR, PAR, NNT flows from those 4 cells. Know the layout cold. Label A, B, C, D correctly every time. 2. RR for cohort, OR for case control. The linkage between study design and measure of association is tested repeatedly on the ACVPM exam, directly and indirectly. When you see a case control study, your default measure is the OR. When you see a cohort or RCT, reach for RR. 3. OR overestimates RR for common outcomes. The rare disease assumption, when the outcome prevalence is less than 10%, is when OR approximates RR. Above that threshold, OR inflates. This matters for interpreting published studies and for selecting the correct answer on the exam. 4. Absolute measures drive public health decisions. AR, PAR, and NNT quantify impact in absolute terms. PAF tells you how much population-level disease could be prevented by eliminating an exposure, and it's driven by both RR and exposure prevalence. 5. Confidence intervals tell you precision, not truth. A CI that crosses the null, 1 for ratios, 0 for differences, means non-significance. A narrow CI means high precision. But precision is not validity. A biased study can be very precise and very wrong. And that's a wrap on our module. You've just worked through every major measure of association and effect that will appear on your ACVPM board exam. And you did it with a real veterinary example from start to finish. That's not a small thing. If you want to lock these concepts in, go back to the BVDV worked example on slide 12 and try to reconstruct all 7 calculations from memory. If you can do that, you own this material. As always, if you found this material helpful, please like and please describe. Up next, we're moving into study design, cohort studies, case control studies, and cross-sectional designs with a deep dive into the strengths, limitations, and classic board exam traps for each. Make sure you're subscribed and don't miss it. Until then, keep studying smart, keep asking good questions, and I'll see you in the next module. Best of luck, everyone. You've got this.